Hi, AP Calculus students. Welcome to second semester of AP Calc. Only 45 minutes a day, but you're enjoying that to start anyway. I also will be cutting your work in half, right? I don't keep the same amount of work. Here's our first section for semester 2. 5.1, natural logarithmic function. We're using differentiation on the natural log function. Now, first thing I want you to know is notice that your homework actually starts like in the higher numbers. What happened to the earlier numbers? You already did the earlier numbers. Remember, you did a pre-calculus review of chapter 5. There was 4 sections, like a 5.1, 5.3, and you did the pre-calc for natural log functions and exponential functions. You did the pre-calc work for that already. So you've already gone into section 5.1 and you did the pre-calculus in it. And so now we're just going to do the calculus, and that's going to happen in a few sections in chapter 5. Now, you may also wonder, or not, is how can we start with the natural log function in 5.1? Like, isn't the natural log function the inverse of a base of e? And don't we start with a base of e? Actually, no. I think this is very interesting, but I'm a calculus teacher. The natural log function is not just defined as the inverse of the e to the x function, right? We always use the natural log function to undo an e to the x problem, or actually any exponential problem that we are trying to solve. But it turns out the natural log function is not just based on e to the x. It has its own definition. It is its own function. We just couldn't explain that to you until now because its definition is calculus. So I find this fascinating. I hope you do too. So what the natural log of x is, it is the area between the function 1 over t, the rational function. You know what that looks like, right? You could graph the branch for where t or x is greater than 0, right? Here it is here. And it is the area from 1, not from 0, right? Because notice the natural log of 0 is undefined. It is the area between the function 1 over t from 1 to some x, where x is greater than 0. So you're going to see this a lot. The natural log function is not defined for x less than 0, so or equal to 0. And so we'll always have this as part of our domain. So here's a picture, right? Here's the function y equals 1 over t, right? And starting from 1 to just some x I drew here, I colored in the area. So it turns out that this is the definition of the natural log function right here, this area from 1 to some x. So in other words, then, the natural log of 1, right, when we put it into its definition, that would be the integral from 1 to 1 of 1 over t dt. Well, of course, the width of this area from 1 to 1 is 0. And if you notice then, on your calculator, right, that is why when you hit the natural log of 1, right, that you get a 0. Notice if I put this into the calculator also, you would obviously get a 0. Okay, and we'll integrate later and see how the natural log symbols is equal to the area of between 1 over t dt and the x-axis, or the t-axis in this case. Let's check this out and see if this still works. The natural log of 4. I'm going to put that into my calculator. That would be the area under 1 over t from 1 to 4. So the natural log of 4, it appears that that area would be 1.386. 1.386, right there it is right there. 1.386. Well, let's go ahead. Let's put this into the calculator. Let's hit math and integral, right? From 1 to 4, right? Let's get that area. of 1 over x. I'm using x as on my calculator because it likes those best, right? So I actually did the integral 1 to 4, 1 over x dx. And when you hit enter, look at that. It has the same answer as the natural log of 4. It's the same. The natural log of e, you know, is 1. Isn't that kind of interesting? So this area right here, if you start at 1 and go to e, you know, about 2.71828, apparently that area is a perfect 1. So let's go ahead and do that. I'm just going to, we know the natural log of e is 1. Let's go back to our integral, and I'm just going to make that 4 that I had up here in e by just going back over there, overwriting it with an e. There it is. And let's see if we really do. We get a 1. Look at that. Isn't that kind of cool? This also explains why when you put a natural log of a number greater than 0 but less than 1, right, in your calculator, the natural log of 0.5, let's go ahead and put that in. You get a negative value, a negative 0.693, right? Negative 0.693. Look at that. You know, and this makes sense because take a look here. If you start at 1 and go to a 0.5, you are in fact, here's 0.5, right? You are in fact losing area, right? It's a negative value, right? When you go backwards from right to left. Sorry, I'm hesitating. This is like my 4th video today, so I'm really trying to do my best. Isn't that cool? Anyway, so you may ask, well, you're like, well, can't I integrate 1 over t? Like, why is it equal to the natural log? Isn't that a power? Can I integrate that? No, you can't. Watch this. 1 over t squared, you can use the power rule to integrate. Watch what happens when you try to integrate 1 over t, or I wrote as t to the negative 1, right? Here's our problem right away. We add 1 to the exponent and divide by the new exponent. Take a look here. Negative 1 plus 1 is 0. Now I'm dividing by 0. We cannot. I just tripped on something. Oh, here goes. Oh my gosh. That's the first time that happened. I just knocked down the lamp. You can't divide by 0. Isn't that cool? Anyway, that's why the integration of 1 over t is something other than that, the natural log. Anyway, enough with my fascination. Let's move on. So this means then, right, here's a list of all the things this means. It means that because the natural log of the x is equal to the integral from 1 of x of 1 over t dt, it means if I take the derivative of both sides, right, that, and again, I wrote it differently here, leave this form, and then differently, the natural log of x would equal, take a look here, by FTC number 2, this derivative would cancel out this integral, and you would be left with the function evaluated at the upper limit, 1 over x times the derivative of x, which is 1. So the natural log, the derivative of the natural log of x then is equal to 1 over x. Notice that the x has to be greater than 0 because of the area picture we're looking at. And plus, you know that that is the domain of the natural log of x, right? It has to be greater than 0. Notice this also means that if you integrate 1 over x dx, you get the natural log of the absolute value of x. This is very, very important. This natural log of x plus c here. Why is that true? Take a look here. This x can be anything you want, right? Except 0, but it can be negative. Notice that is not true here. This x cannot be negative. So we have to remember the domain of the natural log function. So here we have to say, no matter, you know, this x was negative or positive here, it's got to be greater than 0, right? And so this also means by the chain rule, if you have the natural log of a function other than just x and you're taking the derivative, it equals the derivative of the natural log of anything is 1 over anything times the derivative of the inside function. Sometimes now that you have done u substitution, they use u's instead. This means that the natural log of u, the book says that that is equal to du over u. You know, I don't like to mix my du in my expression, or u prime over u, or my preferred way, 1 over u du by the chain rule. Of course, u has to be greater than 0. Okay, so let's try some of this, shall we? Let's try number 50. Okay, I'm not, am I in the way? I think I am. Here, let's see. I'll stand over here. On number 50, they are asking you to take the derivative of, so h of x equals the natural log 2x squared plus 1 is anything b squared. And they're just asking us to take the derivative. So we're going to take the derivative. Here we go. The derivative of the natural log of anything is 1 over anything times the derivative of the inside function, which will be 4x. And my final answer is 4x over 2x squared plus 1. That's it. Kind of nice, huh? Not bad, right? Let's try number 46. On number 46, I believe that they're asking for tangent line. Write the equation of a tangent line. I'm going to just go ahead and do that right now. The equation of a tangent line. Right? Given y equals the natural log of x to the 1/2 at the point 1, 0. Okay, so I can put in the 1 and the 0 right now, right? So f of c is 0. There we go. And c is 1. So I'll put in a 1 here and here. Notice I just need the derivative of this function evaluated at 1. Okay. Now I want you to watch this carefully because it is important, not absolutely necessary, but super helpful if you use powers and product and quotient properties of logarithms. Here's what I'm saying. Okay, so this expression here, I need to take the derivative of it and evaluate it at 1. I am saying that I actually see that when you have the logarithm of a solution to an exponent by the power rule, so I'm not taking the derivative here, students, I'm just using a power rule. I can bring, because of the natural log, I can bring this 1/2 out front and multiply it by the rest of the log by the power rule. Sound familiar? Okay, now I'm going to take the derivative. The derivative would be, I'm going to carry my 1/2. The derivative of the natural log of x is 1 over x. So easy derivative when I use the power rule. I'm going to evaluate that at 1, and I get 1/2. Okay, that means this 1/2 goes right here. Okay, 1/2. And there is my final answer for the tangent line, right? All right. Now, let's remember that when we use the power rule, we had the derivative right here. What happens if you don't use the power rule of logarithms? Shouldn't you get the same derivative? You do, but watch how it's more difficult. Okay, let's go ahead and do it. So let's start with the expression they gave us right here, and let's not use the power rule, and let's take the derivative. Are you ready? Okay. All right, I have a square root function inside my natural log function. The derivative of the natural log of anything is 1 over anything. Times the derivative of the inside function. I'm going to bring the 1/2 out front and multiply it and reduce the exponent by 1. That is an x to the negative 1/2. I am going to put it in the denominator as a positive 1/2, right? Take a look. What do I have here? 1 in the numerator, 2 in the denominator. X to the 1/2 times x to the 1/2 is x. So notice that I do get the same derivative, but wasn't that a lot more complicated when I didn't use the power rule? So Use product rules, quotient rules, power rules for logarithms to help yourself simplify expressions, okay? Let's take a look at number 60. By the way, those rules will help you on the AP exam. They will have those rules show up, and it would be easier if you remembered them. On number 60, they want the derivative. H of t equals the natural log of t over t. Okay, and they want the derivative. I believe I need the quotient rule here. I'm going to talk my way through it. Okay, for the quotient rule, I take the derivative of the numerator times the denominator minus, I'm going to keep my numerator, multiply it by the derivative of the denominator all over the denominator squared. There we go. Notice these t's cancel out, and I am left with 1 minus the natural log of t over t squared is the derivative. Okay, just really quick, I can't remember what I assigned, but if I assign number 55, you may want to use the product rule for logs to help yourself out there to split it up. And you, if I gave a problem like 57, you may want to use the quotient rule for logs to split it up before you take the derivative to make it easier. Okay, let's take a look at number 85. This is implicit differentiation. Remember where you have your x and your y's and you're taking the derivative with respect to x. So what you're going to find in these next sections is all kinds of work you already know how to do. Derivatives, tangent lines, implicit differentiation, max and mins, inflection points, all the things you already know, but now they have the natural log in them. And so this is great practice for all the things, all the operations that you've already learned to do. Okay, so they're asking us to find dy dx. Okay, so I know I'm going to take the derivative of both sides with respect to x. And then if there's a y, I will take the derivative, but I have to multiply by y prime. Before I do that, I see something right here. Not that this wouldn't be difficult to take the derivative of, but I think I'm going to use the power rule and rewrite the natural log of y squared as 2 natural logs of y plus 2y equals 2x before I take the derivative of it. I think it would make my work easier. Let's go ahead and do that. Okay. So here we go. The derivative of 4x cubed is 12x squared plus the derivative of 2 natural logs of y is 2 times 1 over y times y prime. So I carried by 2. The derivative of the natural log of y is 1 over y times y prime plus 2 times y prime equals 2. Okay, let's get the y primes alone. I'm going to subtract a 12x squared from both sides. There we go. I'm going to factor a y prime. And that leaves a 2y plus 2. I'm going to write that as 2 over 1 equals 2 minus 12x squared. All right, so I need to divide by this expression to get the y prime alone. I'm not liking it. I'm not liking it because I don't have a common denominator. I can't flip 2 different fractions over a plus sign. I can flip one fraction, right? So let's get a common denominator. I'm going to multiply the top and the bottom here by y. There we go. And I'm going to rewrite it as 2 plus 2y divided by y equals 2 minus 12x squared. There we go. And when I divide here, it will be the same as multiplying by the reciprocal, right? So the y will be on top over 2 plus 2y. So this answer is perfectly correct, except for that I can factor a 2, right, from everything. So if you notice here, I've kind of run out of the room, is what I've noticed, is I will rewrite this expression, factoring a 2 from the first term. That would leave 1 minus 6x squared times y in the numerator. And when I factor a 2 out of the denominator, there we go. I can cancel these 2's. And here is my final answer. All right. Lots of work there. Number 92. Okay. On number 92, they give you an expression and they ask for you to find the relative extrema and inflection points. Relative extrema are maximums and minimums that occur where the derivative is 0 or undefined, not at the endpoints. So let's take a look. As soon as I see they give me this expression here, y equals x minus the natural log of x, I do remind myself that x has to be greater than 0 because of the domain of the natural log function. All right, max and mins, let's take the derivative. That would be 1 minus 1 over x, and we want to know where the critical points are, where this is undefined and where this equals 0. Well, undefined would be where x is 0, but we already said the domain is greater than 0, so this is defined everywhere. Where is this expression equal to 0? Where x is 1. If I put a 1 here, where x is 1. Okay, let's do a little first derivative chart and see if that's a max or min. There we go, interval. Our domain is starting greater than 0. I get stopped at 1, and then from 1 to infinity. Let's do a test value of 1/2 and 2 of the derivative. Then let's see what we have. When we put a 1/2 into the derivative, that's 1 minus 2 is negative. When we put in a 2, that's 1 minus 1/2 is positive. This is a minimum. At 1, and let's put the 1 into the function. 1 minus the natural log of 1 is 0. 1 minus 0 is 1. So we found a minimum. Let's find any inflection points like they asked for. So the second derivative would be 0 here. And when I take the derivative of this expression, this is really negative x to the negative 1. Here, when I bring a negative 1 out front, it is now positive, and reduce the exponent by 1. That is an exponent of a negative 2 or a positive 2 in the denominator. Critical points, undefined at x equals 0, but the domain is greater than 0. Where is this equal to 0? Nowhere, right? What would make this fraction 0 is when the numerator is 0, and it never is, it's a 1. So there's no IPs here. There you go. So I hope you enjoyed section 5.1. Have a great day.